All right, so to start the talk, maybe let me just briefly introduce myself. So I'm Qipeng Liu. I'm from UC San Diego. I'm mostly think myself as a theoretical computer scientist. So I play with math a lot, although it's like a different math than like most of the people think of. So still we are proving things in a formal way, but we use different languages. So here in this talk, I'm going to talk about some recent development on quantum cryptography. So quantum cryptography is different than you might think of. Okay, so all right, so let's give just two examples. I think those are the examples some of you are very familiar with. So one of the example is the Shor's algorithm, which factors integers in polynomial time. So factoring is considered to be one of the most difficult problem without quantum computer. So that's why we, as cryptographer, we build all the applications. I mean, like 20 or 30 years ago, we built almost everything based on factoring. So because it's so important, when quantum computer comes out, it almost breaks everything. It breaks like RSA encryption, gamma encryption, all kinds of digital signatures. So it's really make us rethink the foundation of our modern cryptography. And that's why we also have, like a rich collections of different assumptions based on different mathematical objects, which I will talk about that later. So that's about the challenges that brought by quantum computers. And on the other hand, quantum information and quantum computation, it also brings unique opportunities for us to build things. And one of the most famous example is so-called the quantum key distribution. So what's key distribution? It's a task where we have two parties, Alice and Bob, and they stay on an insecure channel. Everybody can stay on the channel. They can listen to the channel. Usually we call them Eve, stands for eavesdropper. So the goal of key distribution, secure key distribution, is to let these two parties establish a key, a secret key. So later on, they can use the secret key to encrypt messages. And because the messages are encrypted, it will be safe against the eavesdropper stays on the channel. Okay, so this is the so-called the key distribution. So it's really important. It is considered as one of the most important and basic goal cryptographer needs to accomplish. But even in this is like a super fundamental task, we still need to assume certain assumptions. For example, factoring is hard, or finding a short vector in a lattices is difficult. They are computationally intractable. So those are those are the key distribution problem. But the interesting thing is, with the help of quantum information, we can just make a little bit change to this picture. Let's assume we can exchange quantum information through the channel. So previously, we are only allowed to talk to each other classically. Then suddenly, the picture changes. We can do the whole task without assuming anything. Okay, so that's really fascinating. So previously, people are worried about like what happened if our assumptions fails. And turns out, with the help of quantum information, when we can communicate, when we can talk in a quantum language, then suddenly we can do it very, very safely. Okay, so those are the examples where quantum can bring us the opportunities. Okay, so those are the two famous examples. So from my point of view, there are different timelines of our quantum technologies. And indeed, I think they all have very rich interaction with cryptography. So I will divide them with these three different categories. I will call them post-quantum, cryptographic with NISQ devices, and then eventually cryptographic with full-scale quantum computers. Okay, so just remind you again, NISQ stands for Noisy Intermediate Scale Quantum, which basically describes what kind of quantum computer we have right now. So just like a couple hundred of qubits and not stable enough, and we are not able to do any meaningful form of error correction on top of that. Okay, so let's talk about each category briefly. So the first one is post-quantum cryptography. So this is the era roughly happens like 20 or even 30 years ago. Well, we realized the power of quantum computing. And we realize how it can significantly reform the foundation of our modern cryptography. Okay? But still, we don't have a quantum computer, and we want to come out with some solutions to it. Okay? So first example is Shor's algorithm. As we discussed before, lots of things relies on Shor's algorithm because it can factor integers in polynomial time. So it kind of breaks everything. So, you know, like when I've heard the story when Shor proposed the algorithm, like a lot of people just call to each other and they want to see like what happened and what they need to do. It's like a really, really urgent task. And this leads to a lot of rich discussions about what kind of post-quantum hardness we could hope for. Because cryptography is basically looking for hard problems, hard computational problem. And we want that problem to be post-quantum, okay? So those are some candidates like based on problems in lattices. You probably heard about some paper claiming, I mean, there's like always paper claiming they have like an algorithm for lattices, but still most of them are wrong or they made some limited progress. So still we don't know whether lattices are post-quantum secure or not. I mean, we shouldn't know because we have NP versus P problem. So if we know, then we break that, right? We know an answer to that. But still, we have a lot of study trying to understand, giving us more evidence about whether lattices, like any problems in lattices are post-quantum hard or not. There are a lot of different other categories like code-based cryptography or isogeny-based cryptography or anything based on like group actions. So, or anything you can name it. So this is like a general, very interesting story, or not just a story, like a principle that is when you start your studying or your mathematical object, you may at some point realize a certain problem is hard to compute. And you can maybe put some effort and think about it. And maybe after, say, a week, you didn't know how to do it, then this may become eventually a very useful assumption you can use to build cryptography. So here I left a blank for you to fill out. So you can name anything you would like to have. And eventually, you need something which is post-quantumly hard and has some algebraic structure you can build cryptography. Okay? So those are some consequences from Shor's algorithm. And another thing is the Grover's algorithm, which can do brute force search quadratically faster than any classical algorithm. Okay, so for example, let's assume we have an encryption scheme which is secure against a classical brute force attack with running time 2 to the 64, then you can simply, let's assume you have a good quantum computer, then you can run that same attack, a quantum version of the attack, and only cost you 2 to the 32 units of time, which is still exponential, but 2 to the 62 is often considered to be very practical. Let's assume like every unit operation only takes like a millisecond, then this would be very easily to run on a robust quantum computer. So it's considered to be broken. Okay, so those are kind of the landscape of post-quantum crypto. We need to understand all this impact of this quantum algorithm to modern cryptography. We want to examine the post-quantum security of almost all the existing cryptographic protocols, and we want to see what, if they are not secure, what would be our countermeasures. Okay. So those are the first category, post-quantum cryptography. Okay. So the next one is about cryptography with NISQ devices. So I've talked about this Shor's and Grover's algorithm. Although I think we do see progress made towards building a full-scale quantum computer, but still none of these are able to run any of these algorithms, right? So it's interesting to see that, let's assume we only have those limited resources. Then what would be the consequences of those NISQ devices? So because we only have quantum computers with bounded memory, with shallow depths, with unstable, noisy memory, what are their power? Because cryptography is a topic about we trade efficiency for security, right? So what if those quantum attacks nowadays are not very powerful? Should we still sacrifice all the security, all the efficiency just for that security? So that's an interesting question we would like to answer. It's not only important for cryptography, but it's actually important for us to understand the power, especially the near-term power of our quantum computers. Okay. The other direction is to understand, can we build something based on the limited power of quantum computers? Say it's short, the memories are short-lived, it's low depth, can we build something? So one of the most interesting application I already talked about is the quantum key distribution. But indeed, there are things more than just quantum key distribution you can build in the era of NISQ. So which I don't have time to talk about, but the goal here is to find interesting applications even with NISQ devices. Okay, interesting, especially for this talk, interesting cryptographic applications with NISQ devices. All right, so the last one category is the full-scale quantum computer category. So with the full power of quantum computers, let's assume it's noise tolerant, is pretty large scale, and we can eventually take full advantage of quantum computer, right? So as a theorist, we usually dream about having a full quantum computer, and we dream about what's the craziest thing we can do with quantum computer, and that's like the topic on this slide. So here I want to emphasize one important property about quantum information. That is the no cloning principle. So very informally, no cloning principle says that, so if you are given a quantum state, you don't know what the quantum state is, then it is impossible for you to perfectly duplicate a quantum state. Okay, so it's rough, kind of informal, but that's give you the idea. Okay, so this property gives rise to many interesting applications. So they are pretty theoretical. They are still far away from being built, but they opens up a lot of interesting possibility. So one application is called quantum money. So quantum monies are banknotes that are that cannot be cloned due to the law of nature. Okay, so it's completely different from your banknote, because I just give you a banknote of $20. Can you duplicate it? You would say no, because you are afraid of law enforcement. But this is because, right? So it's the unclonability comes from the law of the nation. It's not come from the law of the nature, right? So what we want to do here is we want to amplify, leverage the no cloning principle to different objects, and we want to build interesting application like quantum money just based on the law of nature, okay? Which I will spend more time on this on the following slides, okay? And what makes this even more interesting is we can build on this to get different applications that's even richer than quantum money. For example, something called software copy protection. So you can think about like programs are encoded in a quantum state. So with the help of that quantum state, a description, then you can run a classical program. You can think about it as a function. You input any classical input, you get the corresponding f of x from your evaluation procedure. And there's no way for any adversary, dishonest party, getting that piece of quantum program, duplicate two, and each of these are able to function in the proper way, output the correct evaluation result. So that's something that's something impossible with only classical information, but possible with the combination of cryptography and quantum information. Okay, so this is the last slide. So this is, to me, the rough landscape of quantum cryptography. I would say the intersection between quantum and cryptography is really rich and has a lot to be explored, even in different eras of quantum technologies. So in the rest of the talk, I will talk about the unique property, the no cloning principle, and the quantum money. Just give this as an example about like what is the state-of-the-art way you can construct that in a very abstract, in a very abstract way. I will still use the notation from quantum information to give you the example, but I will try to minimize that, okay? And we'll see what are the problems which mathematicians may be helpful and may be able to contribute. Okay. So as we just mentioned, this no cloning principle, I give you a quantum state. There's no even unbounded machine can produce the same copy of the state. Okay, so here's some catch. So this is an informal statement. So when we use the statement, we really need to give a more formal statement, meaning like how much you can copy, right? Because maybe you're saying you cannot copy the state with 100% chance, but maybe you are able to copy the state with 99% 99 accuracy. That's still not an acceptable result or acceptable baseline, because that kind of means all the protocol you based on that will be, almost always copyable, only very rarely not copyable. So that's like some statement we need to look at. Okay, so with the no cloning principle, we are interested in build a quantum mining scheme. And here we are mostly focusing on something called public key quantum mining. So what does that mean? That means it's a banknote. It's not, like no one can copy the banknote, but also everyone with the banknote are able to verify it. Okay, so in contrast, there's something called the secret key quantum mining. So it's still a banknote which cannot be copied, but only the bank who made the banknote are able to verify it. So that notation is definitely subsumed by a public key quantum mining, and it also has some disadvantages. For example, when you want to do transaction, you always need to send the banknote to the bank. Then I don't think it offers like a lot of interesting properties to make it quantum. So what we wanted to have is a public key, quantum mining with public verifiability. So everyone get that, can doing some operation and see, yes, this is valid. And also remember, you don't want to destroy it when you after the verification, because then it disappeared, right? Okay, so this is a proposed scheme. Say we have any form of unclonability. How about we just set our banknote to be this sheep state, right? That's a possibility. Because we know it is unclonable. Let's assume it has certain very nice unclonability property. So what's the problem with setting a money state with this sheep state? So the problem is really about the public verifiability. So having an unclonable, no cloning principle doesn't tell you anything about how to verify the state. There's not a specific description about the structure on the quantum state, and doesn't help you to do verification. So that's really the problem. Okay, so the very first solution was proposed by Aris and Cristiano about 12 years ago, and they proposed something called a subspace states. So now we will become a little bit more formal, but still everything is like linear algebra, so don't be afraid. So this is a subspace state, a hidden subspace state. So this notation, cat A, is basically stands for the state, and A is a random linear subspace of dimension roughly n by 2. So you can think about the ambient space has dimension n, so you just pick a random linear subspace of dimension roughly half of the whole space, okay? And you just create such a state. Okay, so you don't, if you don't understand this notation, you don't have to. So, but if you do, then this, I think reading this notation will be even easier. Okay, so this is kind of like what the state does. So you can think about the state is a two-dimensional object sitting on this plane. And the interesting thing is when you measure through the x-axis, or more formally the standard basis, then you will get a random vector in the linear subspace A. Okay, so when you look at that through the x-axis, you will get a random vector in A. And what makes it more interesting is if you look at the state in a different direction, through the y-axis, usually we call it the Hadamard basis or the Fourier basis, depends on what number you are playing with. Then you will get some information about the orthogonal subspace, A perp. Okay, so the definition is simply like every vector in A perp will be orthogonal to every vector in A, and naturally it is a linear subspace, also of dimension n by 2. Okay, so this subspace state has very interesting algebraic structure, very simple, but also it enables you to do a verification. Okay, Okay, for those who are familiar with the notation, then if you apply QFT on the state, you will get everything orthogonal to it. So you got a subspace described by a perp. Okay. All right. So with this state, the no cloning principle about this state is the following. So given the state, for whatever quantum machine you give me, it can even run in unbounded time, then it is infeasible for you to get a vector, two vectors, one in the original subspace, the other one in the orthogonal subspace. So this is the property that we will rely on. Okay, so first of all, it's not even something about cloning, right? It's just, can you read information on both of the bases, both of the axes from the quantum state? So in other words, you can interpret it as an analog of uncertainty principle. So basically, it says one cannot know both the position of the speed of a particle with perfect accuracy. So here you can kind of like say, yes, A is like an analog for the position, and a perp is the analog for the momentum or the speed of the particle. So it's kind of that, like that. So you can also think about it as the quantum state A has two incompatible information. One is about information in A, one is about information in A perp. And there's no way for you to extract both of the information. And that is crucial for you to build quantum money. And finally, why this uncertainty principle is a form of unclonability? Because it implies unclonability. So think about this way. Assume you can clone the quantum state. Say, given A, you got two copies of A. Then you can, of course, use one copy. You measure through the x-axis to get A, to get a vector in A, and you measure through the y-axis to get a vector in A perp. So that's a contradiction. Because you can't do this, so you cannot clone. This is indeed a stronger property. Okay? And how do you construct that? Construct the quantum money. You just rely on the subspace state A, and also to verify, because we want public verifiability. This is like the most troublesome thing for us. What we do is we will, associate with two programs. One of the program is checking whether an input vector is in A, and the other program is trying to check whether an input vector is in A perp. Okay? And then to verify, it becomes very simple. You simply run the program O of A on the subspace state cat A. And because we know it has superposition on all vectors in A, it will always return you yes. And then you can look at the Fourier basis, the y-axis, and you run the other program on a quantum state. And you will also always get yes. So this is a way you can verify whether the quantum state is valid or not. Okay, so this seems to propose a very good solution to the question. And also, it's in the paper like 12 years ago. Why we are still care about this, right? That's a big question you would like to ask. So it proposed a lot of limitations, indeed. And until now, we know very little about how to overcome those barriers. So one of the main limitations is we need those classical programs to verify the quantum state, OA and OA perp. But you need an obfuscated version of this program to verify. Why is that the case? Because if I write a classical program, say in Python, in C++, simply describe the structure of A, then you can prepare the state yourself. There's no secret hidden in the quantum money. You can, given the program, arbitrarily duplicate the quantum money. So that's a problem. So therefore, it requires you to have a very, very strong form of program obfuscation. So as a cryptographers, we do have a lot of different, strong form of program obfuscation. And for this particular application, we use something called indistinguishability obfuscation. You don't need to remember the name. It's just like basically the strongest plausible obfuscation that can exist in the world. Okay, so it seems to solve the problem. So it was proposed by Zandri in 2018. But there's still a problem about this particular construction. So first of all, this is a very, very strong form of program obfuscation. It becomes extremely inefficient. So if you only want to even encode a so-called a point function, so it returns 1 on certain point and it returns 0 on every other point, you need like terabytes of memory, and it runs in 2 days. So that's definitely not practical at all. And what makes it even more problematic, I mean, I'm a theorist. I don't care about it takes like whatever memory as long as it's polynomial, right? Polynomial can be n to the 1,000. It doesn't matter to me. But what makes it even more problematic is there's no post-quantum candidate for indistinguishability obfuscation. So it's completely, when we prove things, we will assume we have certain building blocks, and it gives you that. So the theorem is perfect, but we don't have a good candidate for post-quantum indistinguishability obfuscation. Okay, so then this is like the question we are struggling for many, many years, and we still do not have a very clear answer to it. So first of all, do we have any post-quantum candidate for program obfuscation? Okay, so maybe like can you build that from lattices? We don't know. Like lattices is one of the main source of getting post-quantum crypto. We have no ideas about it. Or another more interesting question, I think it opens more possibility is, let's just forget about program obfuscation. Let's forget about even subspace states. Let's try to think about if there's any other quantum states that possess more structures based on some other mathematical objects. So basically, we want this quantum state to still preserve some form of unclonability or uncertainty principle, and it can be publicly verified because the interesting algebraic structure or whatever structure on the quantum states. And eventually we'll want to, based on the quantum state, we want to avoid program obfuscation because that's like the most trouble comes from. Okay, so here are some candidates, but I think people are really tried very hard, and currently we don't have any good option based on lattices, hash, isogeny, anything like cryptographer used frequently. So it's really your time to think about, like what is the computational problem you don't know how to compute, and is that possible you can turn that into something interesting, any cryptographic applications. Okay, so I think I have maybe 1 minute because we are late for 1 or 2 minutes. So this is like a brief history about building and breaking quantum money. So it's all the way from 2009. I'm not going to read everything. But either they are broken after a year of the publication, or there were not enough study on this. Okay, so I think there are still like a lot of publications that will be coming soon, but this gives you a feeling about like how difficult people are fighting with each other. They come up with an assumption, some mathematical assumption, and another group says, okay, we have a way to break your assumption. This is like there's an efficient algorithm, so people are just fight back and forth. And it also proves that this is really important, but also a difficult question to answer. We may need some new insight, okay? So I think I'm running out of time, but this is the 3 categories and some interesting questions I listed. I mean, there'll be like maybe 100 times more than what I listed here. It depends on my personal taste, but I would say it's like a lot of things you can explore, and this is really an exciting area you may want to work on. Okay, thank you.